Good evening and welcome to another edition of Forecast Lab. There is nothing at all going on here weather-wise, so I'm not even going to discuss the aerial footage. It's clear. Well, from the standpoint of the southern U.S., this is a very boring weather pattern, and that's typical of these La Nina seasons. Yep, very dry and boring weather in the south, active in the Great Lakes and British Columbia, and a prevailing northwesterly flow into the northern plains. And as a result, we tend to get cold weather in the northern border regions. The winds are picking up on the Great Plains in response to strong pressure falls out on the high plains, and as a result, we're getting winds up to 40 knots there at Wichita and as high as 46 at Manhattan, Kansas, in the Topeka area. Also, we've got this front here. We can barely pick that up. You can see in the wind field, there's not much indication of anything going on. South winds around Sacramento and Reno, south winds on the other side, and temperatures not really that cold, just 50s and 60s in the northern San Joaquin Valley. But we do see a different picture if we go to the upper air charts. Here we have a polar front jet coming on shore near San Francisco. The main trough axis just offshore, and the ridge axis has moved into the Canadian prairies. So we would expect to find a baroclinic system right in this area here, possibly with a cold front stretching southwest and a warm front the other direction. So that does tend to support what we see here. And here's another potential solution. I think this is probably closer to what's happening. Now, if we draw a cross-section from the cold air down to Arizona, we can do that on tropical tidbits, and let's do that. That should cross right through that jet stream axis. The green lines indicating isotropes, potential vorticity, the purple lines indicating wind speed, and the blue and orange shading indicating potential vorticity. Now, one thing that's important about potential vorticity is parcels tend to conserve that value. Now, typically we find high values up in the stratosphere and low values down near the surface. So if we're finding yellowish and red high values down here, that indicates it probably descended from the stratosphere. And consequently, that suggests that we're finding downward motion on the north side of the jet and upward motion on the south side. And we can see this tropopause fold right there underneath the jet, and that's located over northern Nevada. So most definitely the front is south of there. This is a closer look at things, and wow, look at that 51 knot reading. That's going to be at Desert Rock near the Department of Energy site. 51 knots, that's going to be about 58 miles an hour. And if those high winds are not from convection, which they are not, that indicates we've got a powerful weather system in that part of the country. Also, we see the northwest winds right there at Barstow. So yeah, I would certainly bring that front maybe a little further to the south. And there's what the visible satellite looks like in California, Nevada, Arizona, and Utah. We normally don't see this kind of cloud material in the San Joaquin Valley ahead of the front. Typically ahead of the front we see a lot of strong solar heating, warm temperatures, and an assortment of high clouds. But here we've got multiple cloud layers. We've got stratocumulus, altocumulus, cirrus, just about everything. And that definitely points to things being behind the front back there. So the actual location of that front is going to be somewhere in here. And then, of course, that area where we have 51 knots, that's going to be right in here. And I think right there near Mount Charleston, that's going to be standing lenticular altocumulus. There may be kind of a spectacular display there, and I would expect things to be very, very bumpy just north of those mountains. When I worked at the Tonopah Test Range located right there, every week we would fly to Nellis and back Typically we did a route like that, and this stretch right here was always very bumpy when the weather was active in the wintertime. Elsewhere around the continent, this is a map from Tropical Tidbits showing pressure and thickness. Thickness is both the red and blue lines. So what do we see here? Well, the chart looks like a mess, but we can still pick out some very useful information. Notice that the thickness lines form kind of a band, and it goes all the way back here, out in the Pacific, and it picks up again out there in the Bering Sea. Now, keep in mind that the fronts are on the warm side of that gradient. I mean, this is basically a thickness gradient. It's a density gradient, thermal gradient, all the same thing. And this suggests that the fronts are located something like that right there. In fact, this probably sort of connects back up into that Alberta system. Maybe not quite, but the fronts look like that, and then they pick up again off in the Atlantic Ocean, kind of like that. And I think we can find even more fronts out there in the Pacific. That looks like another one, and that appears to go occluded up into the Bering Sea. And this kind of connects back up into that system there. So you kind of see what's going on there. This paints out the polar front that rings the hemisphere. And also with that, we can see the centers of the air masses. Here's an air mass center over Quebec. That's kind of a breakaway from the main polar air mass region. And looks like another air mass region right there off Vancouver Island out in the Pacific. And that's helping to push some cold air onto the west coast and into the Canadian Rockies. So even though the map is a mess, we can see what's going on. This is a very useful image. Maybe we should do more of these. So a quick review from yesterday. We talked about frontal intensity, and that's dictated by the strength, the packing of the thermal and thickness lines, like right here. Now, we haven't gotten as far as drawing boxes. That's the advection thing. We don't even need to be looking at those boxes. Just the packing, the shear packing, that indicates that we have a strong front there. And whether that strong front results in thermal advection, that depends, of course, on the isobaric setup. And we'll just paint out the fronts real quick. And that's roughly what they're going to look like. Now, we're not only interested in the intensity of a front, but the change in intensity. Frontogenesis is the strengthening of a front, while frontolysis is the weakening of a front. One way we can measure that is to look at the thermal gradient change over time. So if we look at this front right here and bring that forward, we can see what looks like maybe a little bit of strengthening. So that would be frontogenesis. Here's an example of frontolysis. This is going to be Saturday the 28th. Looks like there's a front right there moving south through the southeastern U.S. And if we roll it forward, watch the packing right here move south. And you can see that packing starts spreading apart. It gets further and further apart. And then the front just kind of washes out. So that's an example of frontolysis. Here's another example of frontolysis using pivotal weather, and we're going to set the cursor into that zone in northern Georgia. And there you can see the frontal inversion up at about 10,000 to 12,000 feet. Looks pretty strong. But if we follow that flow southward, we can see that later on the soundings show less of a frontal inversion. So that would be a vertical indication of frontolysis. And the opposite is true for frontogenesis. We would see strengthening of that frontal inversion. And we've talked about frontal inversions on previous installments of these dynamics lessons. And that's it for our Wednesday edition of Forecast Lab. Thank you for watching, and we will see you tomorrow. Bye-bye.